All right, we are kind of moving into the tree and graph structure section of our course. We're going to start off with this idea of binary trees, which we explored briefly in a way with our heaps. We used heaps to represent kind of a smushed down flat version of a complete binary tree. So we're going to expand that a little bit to study a very well-known data structure called a binary search tree. And it's really cool. It's like a little machine once you get it up and running, and it's used pretty much everywhere, various variations of it. Quick stuff for the week. So a little update on Lab 11. So if you downloaded it previously, maybe have a quick check. I think I just only did some cosmetic changes to it. So no structural changes to it from what was posted up there before. So you should be in pretty good shape. Next Tuesday, we have our homework 3, which is our priority queue via singly linked list. Please get your links from these from Canvas. It's probably the safest thing to do if you're downloading these things. And of course, our quiz 3 there as well. And you should be in pretty good shape. We're rounding the corner. We really only have, after next Tuesday, we only have 2 more weeks before our midterm. So we'll start talking about the midterm next week. But basically, if you're familiar with my other classes, you'll get a practice midterm the weekend before the midterm. We'll even have a kind of a review day so we can go through the most critical things one more time, try to help folks out. So you'll have lots of tools, and we'll even have, maybe a little less labs and stuff heading into the midterm. So you got some time to prepare for that. So the quizzes are always very formative in terms of what the midterm is going to be. And we'll dig into that a little more next week when we come back. So for today, we're going to do a real quick touch base on the heaps, but then start talking about graphs. Trees are, of course, a subset of graphs, and the graph conversation could go on, but that will actually be a more general part of our studies after we get through our binary search trees. We'll kind of move out into this idea of things that are connected to other things in many possible ways. And there are huge numbers of applications for that. So there's quite a few algorithms and approaches to solving these problems using graphs. For us, though, we're going to zoom in on trees, and in particular binary trees, and in particular something we'll call a binary search tree, which we will explore in detail today. But remember that our trees are kind of rooted at the top, if you will. So from our notation for our class, we think of the trunk of our tree as sort of depth 0, and then we sort of go down. And we tend to do it that way because we tend to recurse or use recursion to explore the structure of some set of connected nodes. And for us today, that's going to be a binary tree, which you can actually see a visual representation of a binary tree there. And then we want to learn about what our traversals are and how we can change our traversal through the tree. In other words, which branches do we go down and in what order by tweaking our code. And we probably have, hinted at that a few times. But there's a depth first traversal, which you can do in a lot of different ways. And then the breadth first traversal, which we talked about briefly with the binary heap. So we'll go into those again today and start looking at the code for actually doing that on a formally kind of linked up node structure instead of our array implementation. So we'll actually start looking at a binary tree implementation today. And there are lots of different variations on how you represent a binary tree. I'll show you mine. We'll go through insertion into the tree, like how do you add a new leaf to the tree or a new branch to the tree. We'll look at doing that first off by just flipping a coin. It's kind of like, hey, do I go left or right if I want to add a new branch to the tree? How do I do that in a way that keeps our tree somewhat balanced? So flipping a coin is one way to do that. It's like, hey, I got a tree with just 2 little branches and I want to grow the tree. And how do I know which direction I would want to go? So we'll look at first random insertion and see what that looks like in code. And then we'll look at binary search trees, which are actually kind of a more useful way of deciding where to put things in because we want to do it in an ordered way. And we'll do something like this, if I have 50 at the top in a binary search tree, everything to the left should be less than or equal to 50. So, and if we looked at that tree over here, you kind of see that that is the case, right? So that is a recursive definition so that everything less than 30, less than or equal to 30 would be over here, etc. So if that holds true for the entire tree, then we would say, okay, that's a binary search tree. And that really is used very often for fast storage and retrieval of data that we know we want to pull out in some order, like a dictionary, or maybe sorting people in a database by their social security numbers or their Moodle number for College of Marin. And so if we have millions of people, we want to be able to find them very, very quickly. And so if we have an ordered structure like this, as you hopefully can kind of imagine now that you've had some exposure to log base 2, you could be like, oh, right. Yeah, the maximum searches I would need to do is going to be the log base 2 of the total number of nodes in that structure, assuming it's a nice, balanced, and filled out tree. So that's why we really like ordered structures like the binary search tree, because it gives us little signposts, left, right, for us to go see if something's in the tree or not. And there's no guarantee that it's going to be in the tree. As you can see here, we don't have every number represented in here, but I know that the maximum search distance I'm going to have to go in that binary search tree is going to be 1, 2, 3, right? Because that's going to be the log base 2 of the total number of nodes that I can fit at that kind of a size of a structure. So that's really the beauty of doing this in a sorted way, is once we build and maintain the tree, we actually have an incredibly efficient way to actually find things very, very quickly rather than a linear search. So instead of searching, in order n, worst case, we're searching at log base 2 of n. And that's really always our goal. So that's our binary search trees. We'll look at all the code and implementation around that. And it'll probably take us about 2 lectures to digest all of that information, and eventually we'll get to ordered insertion probably on our next lecture, but we'll see what we can get to today. So let's just touch base on a few review things. Remember that the really cool thing about binary heaps, which are not fully sorted, is that on average we can achieve constant average insertion time. And so that means that the cost we pay for bubbling up and down kind of averages out over time to a constant value, which really never grows. So our tree gets wider, if you will, and maybe a little deeper, but not really much, such that it affects our performance, which is a pretty cool thing. So we saw that. We said that was kind of a special tree that's kind of left justified on the bottom. And we played some tricks to kind of maintain that. Now, looking back, this is something that is more obvious maybe than some of us might have realized. But half log 2 of 10,000 is the same as log base 4 of 10,000. So if you ran those numbers and you were thinking, oh, I'm dividing my problem for homework through 2, why did I say homework 4? Homework 2 in quarters. Well, that's a pretty intuitive way to think about it. If I divide the world in 4 parts and then I divide that in 4 parts and 4 parts, that's kind of a log-based 4 kind of analysis. So many of you got that answer. Many of you also said it's a half times log base 2. You're not wrong. Same thing, right? So both of those curves give us something which is actually like this purple curve here, which is pretty nice, right? It's actually a nice low sloping curve. So as n gets bigger, we don't end up having a real big growth in our cost to actually find something. Now, some of you found some ways to sort of, trim that down even more. That's really good. But we were mostly staying in a logarithmic type of worst case performance for that particular homework. And again, I think that was homework, I lose count through across all my classes. That was homework 3, I think we were on to there. So or 2. Yeah, that was 2. Right. So I don't know where I got 4 on that. Anyway, Good to know. And we can kind of just wave our hands and say it's logarithmic, right? That's mostly what people are wanting to know when they say, what's your worst case scenario? That tells you we're doing some kind of a divide and conquer thing. Okay. And the N here was the number of statues. So it was the number of rows times the number of columns. So that's where we got our 10,000 from. Okay. So I think most everybody is okay with that. Now, where we're going is we're going to talk about generalized graphs. Now, graph structures, when they're really boiled down, are kind of either directed or undirected. So undirected means you can go, any way you want between any two nodes. So those purple arrows there are kind of implying that it's a two-way street. The green arrows are showing us it's a one-way street. So as we go forward in this class, we will divide our problems into undirected graphs or directed graphs. And so we'll get back to more about what that means. And we'll say we can enter the graph at any place, right? So if we're getting on Google Maps, we want to be able to start from New York or LA or, Denver, we want to enter the graph from anywhere and start exploring. So there's no real route to a true graph structure, okay? And a lot of them are cyclic in nature, which means you can kind of leave one node and get back to where you started from. And that's what we would call a cycle. Okay. So trees are not cyclic in nature. Of course, you probably kind of have an intuitive sense about that. And in a tree, the edges are kind of all directed toward the leaves. We don't assume that we're traveling up and down the tree at all times. We tend to travel from root to tree. So, but here's, the general case with our bidirectional kind of connections versus our directed ones. So lots of cool problems that we can solve with these networks, right? But we want to study trees for the time being. Just a reminder, trees come in all kinds of flavors, not just binary trees. And in particular, you could question whether this is really a tree or not, right? Since we're kind of sharing a node there. But these are generally considered to be trees. And these trees over here, it is still a tree. It's just a really unbalanced tree, right? We're not really hanging anything off of these other potential nodes over there, okay? So we'll see that problem here pretty quickly with some of the code that we're going to write. Now, in terms of notation, we talked about height before. We're kind of moving into the world of recursion again, and we're going to talk about depth. So depth 0 is kind of at the root. Depth 1 for us is going to be the next level and the next level and the next level. And it's a little bit annoying that there's height and there's depth, and the equations are a little different or off by 1 between the two. But I'm not going to really, count off on anybody's test questions on these kind of things. But for our sanity here from now going forward, we're going to talk about the root being at depth 1, okay? And the number of edges from the root to the tree is kind of the furthest depth that we can actually go, okay? So we'll try not to call that height because that tends to get a little confusing, okay? Now, of all the things we can do, file systems, as we all know, are pretty much tree-based, right? We kind of move down through our nested folder structures. There are some pretty cool optimizations for 3D graphics rendering called binary space partitioning, where we divide the world in half, and then every half we divide in half again and again and again and again. And that allows us to kind of draw the things that are in view and ignore the things that are off the screen a little more efficiently. So there's some pretty cool algorithms that are essentially tree-based for that. Decision trees, language and equation parsers, actual graphical representation of trees. So you can, there's some software out there for artists that actually grows trees by literally building the tree structure and following it in a organically correct way. So lots of things that you can represent with those. We're going to be looking at this flavor here where we just have a left and a right child at a maximum and sometimes no children at all. Okay, so this is our data structure, and we'll have a lot of kind of variations on the way we could potentially build that. The special version today is the binary search tree, which I mentioned at the beginning. The binary search tree all of the children to the left have to be less than or equal to the parent. So you can have duplicates over here, potentially, on that left side. And everything on the right side has to be greater than. Okay. And as we'll mention a couple times, duplicates could kind of go either to the left or to the right, depending on your convention. But for our class, we'll keep the duplicates on the left side. Okay, so if there's a duplicate, like a 13, it's going to be somewhere over here on the left, not on the right. So that way we can kind of keep ourselves straight throughout the rest of the course. Okay. So the most children we have is 2, and we may have less than 2. Okay. Now let's talk about traversal. So the main ways would be depth first, which is really a recursive game that has lots of flavors. There are lots of ways to explore a cave system where there's 2 rooms to choose from at every step of the way. We could go left. We could be biased going left, or we could be biased going right. And then there's some other things that we might do differently as we do that. Alternatively, and this is just one flavor of that traversal, right? We sort of go far left as we can. We go back and we're like, oh yeah, I haven't been down this passage. Okay, I'll go right. Then it's like, oh, okay, I'll go back to my left until I can't do that anymore. I'll go up. So you can kind of sense what that would be like in a real cave system, right? You're going to have a strategy so you don't get lost. And so you visit every room. And you're going to visit each room potentially, on the way down and on the way up, right? So we pass through 8 and then we pass back through it and go down and we come back up, etc. So we've kind of seen that in some of the recursion that we've done so far. Now that is contrasted with this breadth first we talked about doing with our binary heap array, but how the heck are we going to do that in code when we have a linked node structure? So for this, we want to do the root, and we want to go sideways. So how are we going to get sideways? We have to go up and down, and then up and down to the left, and it's kind of messy. So we'll see that a queue is really going to be our best friend for traversing a tree structure in a breadth first search. Without that, it's a pretty messy proposition. So those are our 2 main forks in the road in terms of how we might want to explore a connected tree structure like that. Okay. So that's kind of where we want to start. But let's dig into our depth first traversal and see how it relates to the code, because I think probably we've seen a little bit of this code before. But here's our kind of explore left bias, which we tend to call an in-order traversal. Now, what I've got here in front of me is a binary search tree. So you'll notice that although at first glance it doesn't look like much, it actually is very ordered in the sense that, the 1 is the smallest value, the 29 is the greatest. And if I come up with the right traversal, I'm going to visit the nodes kind of in an ascending order. So I got to get to the furthest node first. So I'm going to go as far as I can left. Then I'll kind of explore right through the parent, and then I'll recursively unwind and keep going, right? So the unwinding part kind of takes us back through so we can finish exploring the rest of it. And we just kind of do that recursively over and over and over again. So here's our in-order traversal, right? Now notice I go down 9, 5, 3, 1, and you're going to say, well, that's not really in order. So what are you talking about? But if I kind of have a journal notebook and I write down the rooms in the order of, hey, go as far as left as you can, then write down that room. Okay. Then when you go to a parent, write down the parent's room. And then if you go to a right sibling, then write down that one. So it's not just the traversal, it's actually the order in which we sort of, write down where we went in our journey, right? So in this particular case, we're going to go left, parent, right. And I'll show you that code here in a second. And that is going to result in what we call an in-order traversal. Go as far as we can left, go up, try to go right, then go up again, try to go right, then go left, etc. And that is going to give us a ascending list. And that's the goal with this binary search tree. is we can come up with one way to travel through it, and we'll get our in order traversal if that's what we're trying to get out of this thing. So it's kind of already sorted. So, we want to be able to just travel through it in a very, very specific way. Okay. So the unwinding arrows are really the ones in which we're kind of climbing back up to the surface and may have already documented a room. Okay. So even though we visit the parent twice, we want to find a way to print them out only once. So on the way down, then on the way up, and we'll kind of look at the code for that. Now, here is kind of another way to do that. The idea is go as far right as you can, go up to the parent, and then explore the left child if there's one there. So again, think about visiting a cave system where maybe you're biased to go right, 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 right. You hit a dead end, and then you kind of backtrack and explore to the left as a secondary thought, right? Backtracking, backtracking, go left. It's like, oh, okay, I'm a right-handed person. I'm going to go right till I backtrack, then I'll go left, that kind of thing. So this would get us a descending order if we document these in the correct way, right, from our binary search tree. Okay. And so that is kind of known as so there's an in order search and a reverse order search. And we ultimately, if we're recursing, we got to get all the way back up to the top on that thing. Okay. And yes, we visit every parent twice, but we might just write down our notes one time for our parents. Okay. So here's, again, the journal idea I think is helpful because we know we're going to pass through the parent maybe several times, at least two times in some cases. So it's really about when we decide to print out something on the screen, right? And I'll get to the code here in a second that will make this a little clearer. So we could go across the nodes, or we could go depth first. And the depth first is going to come in a variety of different variations. There's 6 of them to be clear. Like we could document the order of our visitation in a lot of different ways. There's about 6 main ones that we will explore here. Okay. So many of these have very quote famous names, right? So, or very familiar names. So if you go left and then you explore as far as you can, and then you go back up and print the parent and then go back down right, that's what we call an in order traversal. So the parent ends up being kind of in the middle of that. So here the me is the parent one, right? So parent node. And we'll look at the recursive code for this in just a second. If you flip that around a little bit and you move the parent to the top and you write down, hey, I'm in a room with, moss on the ceiling, and now I'm going to go left, right? That's a pre-order traversal because the parent is before the children. So we call that a pre-order traversal. And if we put the parent last, which is a little bit of a weird choice, then just in terms of its utility, we have what we call a post-order traversal. And the out-of-order traversal is really just the opposite of the first one. Okay. So we'll see in code, there's really 2 other flavors of this that don't have names. And no one really cares about them too much. But, when you go out into the world and someone says, do you know what an in-order traversal is? They mean something very specific. They mean you explore left, then you unwind through the parent, and then you explore right. Okay. And, even though these names are not really easy to remember, they're kind of industry standard, I guess you'd say. Okay. So we'll get to the code, and I think that will help you a little bit. But the clue to remembering these things is the in, pre, and post is telling you where the parent is relative to its 2 children when we look at the recursive code. So in order, the parent is in between the children. Pre-order, it comes before. Post order, it comes after. And out of order is just kind of flip the children left and right. Okay. So I didn't make up these names, but I try to come up with tricks to help me remember them as well, right? So we're not kind of wasting brain space. So those are our key names. And you can think of permutations and think, okay, yeah, I could come up with 2 other ones we haven't talked about, and we'll see those here in just a second. Okay. But they're not really thought about much. So once again, let's look at the goal of in-order traversal is first get to the bottom left leaf, recurse as far as we can, And now we're at our base case. And so we unwind. And the next thing we do is write down the parent. So we'll write down the number 1 because we hit the dead end. Okay. Then we will write down the parent. And now we got to explore down the right side. Okay. So we go back up to the parent. Got no right side. So we go back up, and that's the 5. Go down the right side. Can't go left. Go down the right side. And we'll see the code here is, simpler than you might realize. Okay. So those blue lines is kind of what we're writing down in our journal, even though we obviously travel down through the 3 and back up 2 times, right? But we only want to kind of annotate those numbers in this specific order, or document them in a specific order. Okay. So that is our left, right kind of parent or recursive traversal. Okay. Here's the PLR, or parent before. So write down the parent, okay, first as you travel down. And when you finally hit the left, write down the left. And then don't write down anything else until you explore a right child, right? And so that is 953169 would be this pre-order traversal, which you might think, is that good for anything? But you'll find that there are things that we'll do with it that will make some useful results for us, right? But it is a little bit weird to try to pull it out of thin air when you look at a tree like that. But we do the parent first, then the left, and then the right. That's our pre-order traversal. So there's our journal that we have after, all of that exploration of that cave system, okay? Okay, and then the other ones here you can probably imagine, right? Post order says go down the left and right first, and then the parent. So there's no right child there, and the 3 doesn't have a right child, so we skip the R and go directly to the P. Now, next is to go right as far as we can go, right? And then do the P, and then the P, and then the P, or sorry, not the P, because we haven't gotten all the way left. We fight our way down to the left, and then the right. It's very strange, right? But that would be a post-order traversal, okay? Okay, post because the parent comes after the children, left, right children, okay? So we're documenting the children before we document the parent in every case, okay? Visit the children, document them before you unwind and document the parent, okay? Strange, but that's what we call it, right? And then the out of order one is just the reverse that gives us the descending traversal, which is a little easier maybe to visualize if we remember it's a binary search tree, okay? So we're going to look at the code for this, I promise. And it's simpler than remembering all of these arrows and things. But I just want to show you that for all of its complexity, we have very little code to write or even tweak to achieve all of these permutations and even more, right? So it's factorial 3, LPR, LRP, PLR, etc. And the last 2 down there, we don't really talk about too much, but there might be reasons to go through the cave system in that particular order, okay? So we're going to look at all those, but let's look at the kind of the one that stands alone first, which is this breadth first traversal, and just talk about the algorithm. We'll come back to the code for this a little bit later, but I just want to mention it because then we're going to go deep on all this other depth first traversal stuff. So breadth first, the algorithm is, as we said, graphically is moving across the rows, which is a really messy proposition if you really are recursing through some tree structure. So the best way to actually do that is using a queue in a really clever way. And it's not a recursive solution. It's a loop, like a for loop or a while loop, okay? So we'll show you how we're going to do that. And it's a cool trick. We'll do it a lot in some other algorithms. So remember our push and pop, right? So, and we can peek in the front of our queue. So we push things into the queue, and we sometimes call that NQ. We pop stuff out, that's DQ. So what we'd like to be able to do is sort of, pull stuff out of the front of a queue and put something in the back based on what we pulled out of the front. Okay. So let's take a look at how we would actually do that with a binary tree. So we always start a breadth first traversal by putting the root of our binary tree in the queue. Okay. We're going to do this symbolically. We're going to push the 9 and assume that it's kind of like a pointer to the node that holds the 9 so that we can get at its children if we want to. Okay. So in goes the 9, and we imply that, yeah, I can use that to get at the children if I need to. So now we start our while loop. So we seeded the queue with the root. Now we start our while loop. We say, okay, I want to kind of pop what's at the head and then push its children in the back. So we're going to pull out the 9, push the 5 and the 13, and document the 9, right? So we got the 9 out, we're going to print it, pop it, and now we just have the 2 children there. So that's our kind of breadth level 1. Now we do the same. We grab the 5, we push its 2 children, 3 and 6, right? And then we print the 5 and pop the 5, okay? And now we're just kind of following that pattern. And it's a little bit magical. We just take the children of 13, push them in, pop the 13 document, and just keep repeating that process, okay? So when the queue is empty, we know we've managed to process all the nodes in the tree, okay? And that's our 9, 5, 13, 3, 6 breadth first traversal. Okay? So when I first was faced with this, I probably spent an hour or two before I was like, duh, like recursion is not going to do this for me, right? So the queue is really the trick for this, and it's a pretty slick one. And we'll for sure use it in a couple very cool algorithms. If you ever heard of the Dijkstra path searching algorithm, breadth first traversal is crucial. So we'll definitely come back to this when we get to some other applications. Okay. So there's our summary. I won't take you through it again, but it's pretty elegant. And obviously you need to have a queue in order to do it. And since we've kind of had a little experience building queues, it won't be too earth shattering when we got to come back and add this back into some of our more complicated algorithms. Any questions before we move off of the breadth first one though? Okay, all right, just a little trick to have in your pockets. Great interview question, so keep that one in mind. But let's dig into our binary trees and let's start doing some code. So we're going to need a node and we're going to need a left and a right pointer. Now remember in C++, if I want something to be a pointer to a thing, I need a star in there, okay? We just kind of deal with that. So left is a pointer to a chunk of memory that holds a node, okay? So we initialize that to null. And then our constructor, anytime we create a new one, somebody gives us an integer value. In our case, we're going to have integer nodes here. We put it in the value member, and then we could probably leave this out, but I do it again just to remind us that, we want to make sure those children are null for that particular node, and we're off and running. So the way we would create this node given that class is to create a temporary pointer of type star node and then just say temp equals new node. So I'm just saying, hey, that's an address in memory somewhere of some node. Okay, well, new always gives us an address from some creation of a node with a value of 13. So the 13 is, of course, traveling over to our constructor here and going in the I. So now we've got this node with the 13 that's been plugged into the value field, okay? And 2 null children, and off we go, right? So our lab today, we're going to manually kind of plug together these nodes and then do some simple analysis on it. So it won't get any more complicated than that for our lab today. It's just like a tree of nodes all hung together, okay? And as you can imagine, if you have the root, you can recurse through until you hit a null child, and that's your base case, right? And then you unwind and go do something else, okay? Now you can do these two things on one line in C++. So just a little C++ explanation for you. You can say node star temp equals new node 13, and it's the same outcome. So however you like to do it is perfectly fine. And then we can say, because temp is a pointer, we follow it with an arrow, okay? So temp arrow kind of reaches in the box, and then we grab the value attribute, okay? So a little bit of reminder about how we do C++ where we have a pointer. Temp arrow goes into the node, and now we can print out the value. You could also print out left and right, and you'll see an address, a hex address pop out on the screen. That's, where that's going to take you if we try to follow that particular pointer, okay? So that's kind of our basic node structure, and we can build a binary search tree out of that, no problem at all. And many people do a functional implementation of a binary search tree using nothing more than this. But we don't really want our functions floating around in our main.cpp. We want to have another kind of class that wraps around this like we did with some of our other work. So we're going to create a binary tree class that just wraps itself around the head pointer and keeps track of a few basic things like how many nodes do we have. And our constructor is going to be super simple. It's just going to make sure that that head pointer is null. And then we'll have some methods that we're going to explore in class today. Insert something into the tree and maybe print the tree. And maybe that print tree is going to print it in a particular linear order, like in order traversal, something like that, okay? Now I have this special one called Print Tree Geeks. I kind of swiped this code from Geeks for Geeks many years ago and kind of modified it to make it my own, but I want to give them credit. So that is a way of seeing the full tree with our text output. So we're going to be using this for a number of our programming assignments this semester. So I want to introduce it to you today. It's a little hard to read at first, but after a while, it's a helpful debugging tool. So I know it's not beautiful, but it's kind of the only tool we got for that. So that's our how to create a binary tree pointer. So BT is a pointer to an instance of our binary tree that's going to be created on the heap. So it's a dynamic allocation of a binary tree, and it starts out life with nothing in it, right? So there's a head, and then we just have our methods inside of there, essentially, and we can call those methods. So I could say, hey, there's my new binary tree, and then I can say BT arrow, call the method that is inside of the binary tree instance, and insert 13, for example, right? So that's how we call the insert method that's part of the binary tree class, not in any way part of the node, right? And so in theory that, we'll write that and it'll work just fine. So, and we will do that. We'll write that here in just a second. Okay. But that's high level how we kind of are going to access our tree. And assuming we kind of fill it up with nodes, we could say BT print tree or print tree geeks. We'll see that in a second. Okay. Now, there's just one other piece of code I need to introduce to you, and that is this default value thing for arguments. So you'll notice that I have a kind of like, hey, what is it that you want to insert into, right? So I'm going to give an I value, which is my 13, but if I don't give a second argument there, right, that's an optional argument, it's going to be assumed to be null. That's what that default value is telling us. If you don't tell me where to insert it, I will start at the top of the tree and I will figure out, because it's a binary search tree, where to put it. But if I give it a pointer, it will assume that's where I want to start, okay? So this is an additional feature we're going to add into our insert, and it will help us deal with some pointer fix-up stuff. So this is going to pretty much make our code simpler in the long run. Although, I'll let you guys be the judge of that in the end. So I'll just point that out now, and we'll see that in code here very soon. Okay. So now we're not going to worry in this class about cleaning up memory as much as we do in my advanced C++ class, but by all rights, we should delete that and delete that, whenever we're done with our tree. But we're not going to spend a lot of time on that aspect of C++ here, because I know not everybody here came to be a C++ person, and that's okay. Okay. So we'll look at how those things work, but let's look at the notation for the print geeks one. This will help you debug your lab today a little bit. So this is how I print binary trees. Apologies for doing it. So if this is my binary tree, 1, 2, 3, 5, 4, there's the 1. Okay, and this is the root. Kind of that less than sign is kind of showing me this is the root over here. And if you see kind of another less than sign, that means it has 2 children. Okay. And here's the 2, and the slash kind of roughly points back toward the parent. And the 2 has another child over here, but has a null child on this side. So you can see there's no right child over here. So that little nodule, that single quote, is kind of a little clue that there's no child over there. Okay. So eventually this will kind of start to help you a little bit in debugging. I apologize, we don't really have a more graphical way to do it, or I haven't been able to write one so elegant, but that's essentially kind of what we're going to have or be stuck with aside from just debuggers in code, right? So, but hopefully, between that and print statements, we'll be able to get through this okay. All right. So that's just chucked in the mix for us. And we'll see it here in just a second. So bear with me. Okay, so let's take a look at what it looks like. Let's run this program. And I don't think we really need to log into Program IZ today for any of this stuff. But let me kind of open this up and show you what I mean. So this is a fully working program. And you'll notice it's got our node structure. So let me kind of zoom up on this a little bit. And it's nice to see these things work. There's our node structure. It's just what we said. There's our binary tree, just what we said. And we've got a couple other things. Here's insert, right? Insert a 13. If you don't give me the start node, I'm going to assume that you want to start at the head, okay? And if it turns out that the head is null, right, essentially, then I'm just going to plug a new node right in there and I'm done. Okay. So my insert there is relatively straightforward. Okay. Okay. Otherwise, I'm going to try to plug it in on the left child, if that's open. Otherwise, I'm going to try to plug it in on the right child. So I'm trying to keep my tree balanced, right? Okay. You ask me to put it somewhere, I'll put it somewhere. Otherwise, I'm going to flip a coin and decide based on the coin flip where I want to insert it. Okay. So here I'm saying, hey, that's where I want you to insert it. So go down that path because I don't know how long that branch is. So that's a recursive call that is specifying where to continue the search. Go left. Okay. So this kind of explains why we have that second argument up here, right? We're not always going to start at the head. Sometimes we're going to recursively call ourselves and just say, hey, keep going until you find a place to insert this particular value of I, okay? Because I flipped a coin. So when you get there, you're going to probably flip another coin, right? So it's that traveling through the cave system where you flip a coin every time and decide which path to go down to. And eventually we find a dead end, and that's where we're going to plug in our new value of I. Okay. So we'll come back and look at that again, but that's our random insertion, right? But let's just run it. And so I'm just going to start putting values in there in any order. So this is my linear print, right? It's printing out in order. This is going to be my geeks print, which is going to slowly get more elaborate. So 5, I'm going to add another one, 6. Remember, it's flipping a coin every time. So the 6 got inserted as the left child of the 5, right? I'm going to insert another one, 8. This is not a binary search tree. It's just flipping a coin, and you can see we got lucky. So now we got a right child with the 8 over there. We'll do a couple more. So if you just kind of keep doing these, and I'll zoom back so you can kind of see it a little better, it's keeping a relatively balanced tree, right? It's flipping a coin every time and then traveling down that direction to kind of figure out where to go, right? And eventually it finds a null and it plugs it in, right? Or there's a null here. It could have plugged it in on the inside there, okay? So it's not particularly useful for creating a binary search tree yet, but it at least lets us kind of experience what it's like to slowly add another branch to our tree and to do it in a flip a coin sort of way. So the end result is more or less a balanced tree, which is never a bad thing. Okay. So you can kind of just run that and you'll see that we're never getting a printed traversal of more than our root node. And that's going to be our first practice problem here in just a second. We're going to write the code so that instead of seeing the full tree, we just see a traversal order that describes the tree in some particular one of these 6 kind of traversal orders. Okay. But that's kind of, that's fully working. It's good to look at the code because we'll be working with it a little bit and get used to that tree representation, okay? But it's kind of cool that just flipping that coin kind of more or less keeps our tree balanced with very, very little code, okay? Now, let's take a look at the print tree function because this is really the whole point of the lecture here today. So if start is null, well, then just make it the head because that's what we want to print, okay? But otherwise, we are in a recursive call. So if the start is not null, then it's kind of been specified and we're probably several levels down the tree traveling through the cave system. So if I only ever print the value of the current tree and I return, well, then it's not a recursive solution, but I need it to be a recursive solution. So I need to explore left and explore right, but where should I put that code? Okay. So when I call that like that, this is really what's going to happen. Okay. So I could either call it from the head or I could call it from some arbitrary location in the middle of the tree. Okay. So we're going to fill in that code pretty much above or below with the recursive calls. And the order in which we do that will determine the traversal that we're going to take. Okay. Let me get this out of the way here. Okay. So we'll start with that thing, null, and then we'll slowly fill in those recursive calls. Okay. So travel down the left, unwind, print the parent, travel down the right. That's our in order traversal. That's the parent, me, being in between the exploration left and the exploration to the right. Okay. It's a little hard to visualize that whole experience, but we're basically saying is I'm more curious about the left. And when I come back to this level of the cave system, I'll write down what number I see on the wall. And then I'm going to go traveling down the right side. But I'll immediately fall into the left bias again when I recursively jump back in on the next level down. Okay. So I'm fighting to go left as much as I can. And on the unwind, I do the parent, and then I fight to go right, and then I go right back to left again. That is our in order traversal code. Doesn't take a lot, but that's all we really need. If we swap those two, we now have the reverse order, right? We're going to go fight to go right as much as we can, unwind, do the parent, and then fight to go left. So if it was a binary search tree, then I would see a descending printout of all of those nodes. Okay. So it's different than the tree that we're seeing, but it gives us the information that we might be looking for in a very unique way. Okay. So we could also put both of them down below. So if the parent is above all of that, that's our pre-order traversal. Print the parent, explore left, explore right after the unwind. Okay, so that's our pre-order, parent before children. Okay. And then, of course, you could put them both above. And I don't think I animated all this because it was at the limits of my animation capabilities. But let's go and do the code for ourselves, because there's nothing better than actually doing that and just seeing kind of the outcome of that. So let's kind of click into this thing. And the insertion is still random, but let's actually finish the print tree in some order that we think is interesting, and we'll be able to decode it from inside of there. So let me, I got to bring my, I'm going to go over here back to this. So what we want to do is find the print tree. Okay. So we'll work on this together. So I'm just going to say find print tree. Okay. So there's our print tree. Okay. So if start is null, then let's reset start to the head, because we're not at a recursive call. We're starting from the very beginning. If after doing that, we're still have a null tree, then, we got to get out of here, because that means we got no nodes. Okay. So just a little safety valve there so we don't blow up. Okay. Otherwise, what we can do is just recursively call ourselves. So we're going to say print tree, and we're going to use the start arrow left. Okay. So I can say, right, if start left is not equal to null PTR, right, then say print tree, print tree, start arrow left. Okay, like so. Okay, so let me just check and make sure I satisfied my prototype. Ah, thank you, thank you, thank you. Appreciate that. Okay, so that's my left expiration. Then I unwind, print the parent, and then we can go, if the right is not equal to null pointer, then we'll go down the right. Okay, print tree to the right. Okay, okay, and that's it. So let's see what we get from that, if I got that right. Okay. So I'm going to just start, inserting values, and they're going to go in random order, right? So I got my 5, 5. I'm going to insert another one, 6. Okay. So now I got a 6, 5. So in order is happening so far, right? Go left, then the parent, right? So let's insert another one. Let's do it 8. So now we got a balanced tree. So it should be 6, 5, 8, right? So let's go up 6, 5, 8, right? So it's doing that. Okay. So it should, no matter what we put in here, and I'll just kind of back it up here so you can kind of see the tree a little bit better. But our in order traversal 0, 6, 5. And then notice we go from the 5 down to the 3, because the parent should be between these two children here. So we recurse down to the left again, back up, do the 8, go down to the 3. And then on the unwind, we're not doing anything after the last child. We're not printing out anything on the unwind after we've done our recursive right kind of maneuver. Okay. So it is very helpful, if this is very new to you, to go to your print tree and just move these things around, and then see and spend a little quality time looking at the insertion, even though it's random, and kind of matching the correlation, right? So let's just do one of them together. I'm going to swap these two. So it'll be a reverse order kind of thing. So we'll put the left on the bottom. Okay. And we'll explore right first. Okay. So try to go right if we can. All right, we'll just put in some numbers, 1, 2, 3, 4, 5, 6. Okay, so there's our tree, and it's not perfectly balanced. You can see 2 doesn't have a child, but we should get 6, 4, 3, right? Or sorry, 6, 3, 4, right, parent, left. Okay, and then we're back up to the parent. And then we're going to go as far right as we can, and that's the 2, and then go left, and then we got our left child off of that. Okay, and that's our reverse. Okay. If we had inserted these nodes in a logical way, in a sorted way, then we would be seeing an in order ascending list or a descending list if we followed either of these two approaches that we're talking about there. So like we saw in the animation on the slides, you could put the recursive calls below the parent, above the parent, swap them around. You're going to get all 6 of those flavors of the depth first traversal. And a lot of times it doesn't matter what order you do it in. But, if it's a binary search tree, it obviously does, right? We want to be able to get those things printed out in a good order. Okay. So really, like if you are not got your head fully wrapped around recursion, this is a good time to dig in and just spend a little extra time, probably outside of class, just convincing yourself you can kind of trace what's going on there. Okay. And it really, again, it's just about the order in which you do these 3 lines of code. Okay. Okay. And if it was a trinary tree, well, then, there'd be a little more lines of code here, but we only have a left and a right, and that keeps code and everything else more sane. Okay. Questions on that so far? Okay, that's a recursive print tree call to create one kind of linear path through that stuff. So we kind of talked about this. So we have the pre-order. You can move these things around and kind of come up with all those variations, but I won't drag you through that. You guys should take a look at that and try to do the post order as well, like we saw. Okay. Now, we're going to get to, so there's our pre-order, etc. Let's talk about this random insertion thing again. Okay. So we are going to insert into the tree in a random order. Let's look at the code a little more closely. So here's how we create our tree again. So we saw this before, kind of a different layout of the tree. Okay. And we're going to do the random insertion, right? So we're really just flipping the coin left and right. We kind of looked at that a little bit and figured out, we're just going to kind of follow through until we find a slot where we can put it. So we flip a coin left or right, we choose random right, and then we have to keep going until we get all the way to a null node, right? If we're going to insert the tree that way, okay? Now you can see if we were doing a binary search tree, we could get a very unbalanced tree. And that's one of the problems we're going to have to learn how to deal with. Okay. So it's not a binary search tree yet. Okay, but let's look at the code up close. I know we saw this briefly. So if it's empty, then we just plug it in at the start. Okay. Otherwise, try to put it in at the left child or put it in at the right child. Okay. And otherwise, we're going to do our recursive thing, okay? So we saw that a little bit before, but let's take a look at that up close. So here's the second half of that. Otherwise, flip a coin. If it's a 0, right, even number, then go left. Otherwise, go right, okay? We may continue on and on and on, right, until we get all the way to the leaves before we actually find a place to insert that thing, okay? So that's our random flip. Okay. So let's see if we can tweak that code to go always left. And you can probably guess what's going to happen, but let's go in and modify that code and take away the randomness, oops, and just kind of make it so that it's going to go always left. And it shouldn't be too much of a surprise, but let's do it anyway. So we find the insert. Where's my insert? I think I went past it. I should have done my search. Print tree. There it is. Okay. So here's the random portion, right? So if I just say, rnum equals 0, and I force it to go left all the time, okay, let's see what actually happens, right? So kind of put in a number 1, 2, 3, 4, 5. So if it filled out the right child, right? Because it tried to execute this code up here first, right? But then it takes a bias and goes down the left path, okay? So if it finds a child that's empty on the right side, it will fill it in. But otherwise, we're going to have a pretty strong bias to building off to the left side. And you can kind of see what happens. We kind of get this skew where everything is sort of slowly growing off and our tree's going to kind of flop over. Okay. So, we can't obviously go just one way or the other. And we can flip that around and go the other way, and you'll get, this thing kind of growing off to the right side. So we have to do that in a logical fashion based on the parent value, right? So that's really what we're after in the long haul. Okay. So good to just do that to sort of get used to, you know, the problem that we're going to face, which is eventually we're going to have a lopsided tree and we're going to have to do some maintenance, just like a gardener, and prune our branches. So one of the big things we're going to get to here in 2 lectures is how do I rebalance my tree after I've created this nice insertion? And that's really where binary search trees are, doing the most unique thing or the most powerful thing is they're, managing to balance themselves. So, but we'll get to that in due time. Okay. So here's just, the equivalent of what we just talked about, right? All right. So we'll look at how we fix these things next week. Actually, maybe on Thursday if we are moving fast enough. But these are valid binary search trees, right? 11 is less than 13, 10 is less than 11. So you could say, well, it's a binary search tree, but it's not actually going to be very efficient. It's going to be a linear worst case cost to find something in that tree. So balancing is crucial if we want to maintain that log base 2 kind of optimal performance. So the theoretical maximum of a binary search tree is log base 2 if it's all fully balanced. If our insertion algorithm is not very good or we're not doing proper maintenance, as we'll see, then we get kind of a degraded performance. Okay. So that's really where we're going to go, is kind of building those things in this form. And so our lab today is just about getting familiar with the recursive nature of those rules. So when we say that it's a binary search tree, we have what's called an invariant, just like our heap invariant. Okay. And we need to ensure that recursively everything below here is less than or equal to the 9, and everything below here is less than or equal to the 5, as you can probably imagine. Okay. So you want to think about how would I write some recursive code that's actually going to determine whether a given binary tree is valid binary search tree. Okay. So we'll look at that here in just a second. We'll zoom in, but that's the binary search tree invariant. We've got to figure out a way to ensure that that's true. And maybe somebody gives us a tree and says, here, tell me if this is valid or not. Okay. And that's what our lab's about. Again, duplicate values. Notice our 9s. We're going to be keeping our duplicate values on the left side. And notice where the biggest value is. It's tucked in the deepest inside right on the left side of the purple 9. Okay. And the smallest value on the right side is tucked deep on the left side of this subtree here. Okay. So that's always going to be true if we want to find, it's not like that you're going to have a 9 up here. The 9 is going to be down here. Okay. Okay. So that's how we're going to manage the duplicate values. And here's a couple quick questions for you. Is this a valid binary search tree? Not in that case, right? Because we can't have the duplicates on both sides of the 9. It won't actually hold up in terms of a consistent recursive rule, okay? So we want to be consistent with where we store our duplicates, okay? And then this one is not a valid either because the 5 is smaller than the 6. So that subtree there is invalid relative to this. It's valid underneath here if you think about all these things being less, but the 5 is out of place with regards to the 6. Okay. So when you think about your lab today, that might be a useful one to come back to. Okay. And here's one. Let's see if we can spot any problems here. So we've got 9, 5, 6, 9, 3, 1, 13, 11, 10, 12. This one looks pretty good. I think we're good here. Yeah, all of those are in good place. Okay. Okay, everything satisfies the rule, left less than or equal to parent, greater than or equal to. All right, we could be comparing letters, by the way, of course, or words, alphanumeric words. So dictionaries are absolutely stored in binary search trees. So the Python dictionary, for example, and the C++ map is ordered map is an actual binary search tree implementation. So that's a good one. Okay. And I think we're just about that one, of course, is not, because it's not really a valid tree at the end of the day. We're sharing the same node. That's a little bit of a silly example. This one, although it's pretty messy looking, C is less than M, H is greater than C, but is still less than M. F, E, F, G, H, right, is less than the H. G is greater than the F and is still less than the H, right? You know, this stuff's, you guys know how to spell, but that's maybe not immediately obvious, but that would be a valid binary search tree. Okay. I think we're getting to the bottom of the pile here. So here's the one that's not, right? So even though all of these letters are less than the M, we have a violation over here, right? I should be after the H, right? So it's okay right here, but here's where the invalid part happens. I cannot be on the left of that H there. So the recursive part is a little trickier than it might look at first, and we'll dig into that here in just a second. And last one here, 15. So 15 is greater than 11, but it's not less than the 13. So there again, we got a little bit of a problem. Okay, so that's not valid either. Okay. All right, and so we'll dig into the balanced binary search tree process for insertion. We'll do insertion or in order insertion and the rebalancing next time, so you can kind of see how we deal with that. But this is kind of the first best step. Good to get used to this before we actually, you know, kind of get into the more complicated stuff. So when we're searching for stuff, remember, it's possible it's not there, right? We got to go all the way to the bottom to figure out that something's not in the tree. But if it's balanced, then, you know, we didn't have to travel that far, right? We just did it from a log base 2 standpoint of the number of nodes there, okay? Okay, so let's take a look at our lab. So it's simple on the surface. I like this one a lot. We're just going to have a bunch of linked nodes. So no binary tree class in this one, just a parent node and then a min and a max value. And you might wonder, what is that min and max value for? So that's going to tell you recursively what is the maximum and minimum value allowed for that particular subtree. Now, when we're starting out, the min needs to be like, you know, negative a bazillion, and the max needs to be positive, you know, infinity, technically. But we're going to just work with like negative 10,000 and positive 10,000, more or less. So we want to travel down that tree using those limits, updating them as we go, and figure out whether that tree is a valid binary search tree or not. Okay. So if it is not, just return false. Okay. So main is fully written and there's like 4 or 5 test problems there. And I've written a function that will build the linked node structure from a collapsed array. And I'll show you that code here in a second. And keep in mind that a null tree, recursively speaking, is valid. Okay. Kind of like our heap. If you have a single node or a null pointer, that's valid. Okay. So you want to return a valid or true thing. Parent all by itself is valid. A parent is only valid if the left child is less than or equal to the parent's value and the right child is greater than the parent's value. Okay. So we'll keep our duplicates on the left-hand side like we were saying. Okay. And whether children are valid is a recursive question. So you'll have to write recursive code to figure that out. Okay. So almost there. Give me another 2 minutes. So let's take a look at this particular question. And sorry, you please ignore those ampersands. Those should not be there. Okay. And they're not in your code. So you don't have to worry about taking that out. So that's the parent. So when I call your function, I'm going to give you really, really big min-max ranges. I'm going to say, hey, everything's going to be between negative 99999 and positive 99999. And you've got to modify those values recursively. So how does that go? So you're going to travel down the left child, and you're going to update in that recursive call the max to be 50. Okay. So that box is telling you that everything inside of that box better be in the range of negative 9999 to 50. Okay. Otherwise, that's an invalid subtree. And then recursively, if you go down the left child again, we of course update that recursive max value to be 25. So we're slowly narrowing down as we drop down in those child branches until we get to our base case. And the 13 has to be less than or equal to the max, or else we have a violation, right? So 13 there would be an invalid node, and you would return a false, and that false is going to percolate all the way back up to the top and essentially tell us the tree is invalid. Okay. Now let's just take a look on the right side over here at the 95. Okay, so we already know the whole tree is invalid, but let's take a look at this 95 over here, because at first glance, you might not know if it's valid or not. Okay, so this is the one in question. So we pass down 50 is the minimum. Okay, it's got to be greater than the minimum. Okay, so here's the rule up here. It must be greater than the minimum and less than or equal to the max, which I know sounds a little backwards at first. Okay, so the minimum there is 50. The minimum there is 75. Notice the max we just keep handing down is 999. Now we have the minimum as still 75. Okay, but the max is 95. So it is indeed less than or equal to the max, right? And greater than the min. So that one is okay, as it turns out. Okay, but this one blows it for everybody over here. Okay. So that's what we want to do. Code is kind of laid out for you, except for that function call. And you can kind of, if you want to try to imagine a bottom-up strategy, you can, but I'm pretty sure you'll have to change the prototype to do that. But I haven't seen anybody come up with one yet, but I do believe there's a way to do it. And, you know, feel free to do that if you want. So just quick looking at the code, and I'll let you guys get out of here. So here's our setup. Here, get in. Should all be there. There we are. A lot of words, just so you don't have to open Canvas again if you don't want to. But here's the thing to keep in mind of here. So I'm going to send each one of these things into your code. So this is kind of a nice way to visualize what is currently an array, but will get turned into a linked list structure by my functions. So you can test and see, and I've even told you, like, hey, this is okay here. This is not okay. There's that 13 we were just looking at, right? But this 95 is okay. So your code should support this when you do your recursive implementation, okay? So these are all your test examples. Everything's written in main. So I build the tree and I call your function and then give you the test results, okay? So you're going to just finish your implementation of this thing all the way down at the bottom, okay? Which is not a lot of code. It's probably about 15, 10 lines of code, maybe less, depending on how you write it. Probably even less than that. Okay. Questions? Okay. All right. That one's a little gnarly, but have fun with it. And I'll give you hints along the way. We'll talk about it a little more on Thursday. Otherwise, let you guys get out of here, and I'll see you on Thursday. Have a good week. Thanks.